This video will define what an autonomous ODE is, as well as the equilibrium solutions of autonomous ODE, and equilibrium, the plural is equilibria. So here we're looking at equilibria of autonomous ODEs. So first thing is we have y prime equals f of y is an autonomous ODE for this function y of t. And in particular, the thing to point out here is that, it's this function f of y, so you could have pretty much anything over here you want, but one thing you can't have on the right-hand side is the variable t. That's not going to appear anywhere on the right-hand side. All right, so just a few examples of those. We have examples. We have y prime equals y plus 3. There are no t's over here explicitly. It's not t times y. It's not plus 3t. There are no t's. So this is an autonomous ODE. So is this one. This is y prime equals y squared. So is this one. This is y prime equals y times 4 minus y. And this one as well, y prime equals f of y, some function of just y. Right, in contrast, some non-examples would be things like y prime equals y plus t. This is not an autonomous ODE because we have t appearing in the equation, in the differential equation. Same thing here, we have y prime equals sine of t plus cosine of t. That one doesn't have y anywhere, so that's not an autonomous differential equation. Same thing here, we have y prime equals the variable t, the independent variable there, over the dependent variable y. It's not autonomous because t is appearing in the right-hand side here. All right. These actually occur pretty often in physics. Often it doesn't matter kind of what time you start the experiment. There's just a system that is moving around its different parts, and it really, the next thing that the system will do is only dependent on the current state of the system, where everything is. It doesn't matter what time the clock says. It only matters the current state of the system. All right, so that's autonomous ODEs. So then you can also have equilibrium solutions. So an equilibrium solution is y of t equals some constant is a solution to the ODE, y prime equals f of y. So, you plug in that constant, it solves the differential equation. And you're going to have y prime equals 0 in that case, because if you take the derivative of a constant, that's 0, so y prime will equal 0 if a solution to the ODE is y equals a constant. All right, so just to do some examples of that, these will all be autonomous ODEs over here. So we have the ODE y prime equals y plus 3. Well, the equilibrium solution would be y equals negative 3. Right, so if I plug in negative 3, y prime is going to equal the derivative of negative 3. The derivative of negative 3 is 0, so y prime equals 0. So we get the left-hand side here is 0. And then I have negative 3 plus 3 is 0. So this is an equilibrium solution to this differential equation. If we start out at a different points, like 2, it's going to have a much more complicated equation solution. But this is an equilibrium. This is one of the solutions to the differential equation. All right, same thing here. We want to find a constant such that it solves the differential equation. That one's not that bad. So if we pick y is equal to 0, well then y prime, so we get derivative of 0 is 0, so the left-hand side 0. And on the right-hand side we get 0 squared. And yeah, definitely 0 equals 0 squared. That's an equilibrium solution. Another one here, we have y prime equals y times 4 minus y. Well, that one will have two equilibrium solutions. There's y equals 0 and there's y equal to 4. Those are both equilibrium solutions. And then here I just kind of put very broadly, it's all y values such that f of y is equal to 0. All right, so next up we're going to go over the stability of the equilibrium solutions.